Have you ever really looked at the world around you? I mean, the phone in your hand, the car in your driveway, it all started out as just rocks. Yeah, humble rocks. They didn't just pop into existence, they were unlocked through this incredible journey of fire and chemistry. So today, we're going to pull back the curtain on that secret life of metal. It seems kind of impossible, right? I mean, how on earth does this dull, earthy-looking rock turn into the shiny, super-thin aluminum foil you have in your kitchen? This isn't magic, you know? It's a full-on chemical adventure with a bunch of steps. And that whole adventure, well, it kicks off deep underground. So everything begins with mining. We got to get our hands on a mineral. Now, you can think of a mineral as like nature's little treasure chest for metal. Sometimes, if you're lucky, the metal's just sitting there, pure. But most of the time, it's chemically locked up with a bunch of other elements. This rock that we dig up, called an ore, is our starting point. Okay, but here's the thing. An ore isn't just pure mineral. Nope, it's all mixed up with a whole lot of, well, worthless rock and dirt. So our first big challenge is a classic case of separating the good stuff from the junk. And there's actually a scientific name for all that worthless stuff. It's called gangue. That's all the stuff we don't want. The dirt, the sand, the extra bits of rock. It's basically just in the way. So before we can get to any of the fancy chemistry, we've got to get rid of the gangue. And this whole cleanup process is called concentration. The goal here is pretty simple. We want to boost the proportion of the valuable metal-bearing mineral by ditching as much of that gangue as we possibly can. Seriously, just think of it like panning for gold. You're just washing away all the sand and dirt to get to those shiny little flakes. And this is where things get really ingenious. Metallurgists basically use the physical properties of the mineral and the gangue against each other. So if the mineral is heavier, they just use gravity to separate it. For some other ores, they use this really clever, bubbly froth to float the good stuff right to the top. And sometimes the solution is as elegant and simple as a magnet. Take magnetic separation, for instance. It's a perfect example of how simple physics can be so incredibly powerful. You just drop the crushed ore onto a conveyor belt that has a magnetic roller at the end. The magnetic mineral particles, they cling to the belt for just a split second longer and fall into one pile, while all the useless gangue just falls straight down into another. So simple, but so effective. All right, so we've concentrated our ore. We've got a much higher percentage of the good stuff now. But that metal is still chemically locked up. So for the next stage, things are going to get really hot. And I mean that literally. It's time for the trial by fire. Now, here's the crucial point. It is way easier to get a pure metal from its oxide form, that's the metal bonded with oxygen, than it is from its original state. So our next job is to turn that concentrated ore into a metallic oxide. And we do that with two main heating techniques. The two key processes here are roasting and calcination. Now, they both use intense heat, but there's one huge difference: oxygen. Roasting is done with a ton of oxygen, which is just perfect for sulfide ores. Calcination, on the other hand, is done without oxygen, and it's used to break down carbonate ores and drive off all that carbon dioxide. Okay, so we've got our metallic oxide. Now it's time for the main event, reduction. This is the moment we've all been waiting for. We need to strip that oxygen away from the metal. A lot of the time, this happens in a giant furnace in a process called smelting. We add something called a reducing agent. Very often, it's carbon, which basically wants the oxygen more than the metal does. The carbon just swoops in, grabs the oxygen, and leaves our beautiful metal behind. But get this. Here's a really fascinating little twist. Sometimes you don't even need to add anything. For certain metals, like copper, the ore can pretty much reduce itself. It's this amazing process called autoreduction. What happens is the copper oxide reacts with copper sulfide, and they just kind of swap partners, producing pure liquid copper and some sulfur dioxide gas. It's like chemistry doing all the heavy lifting for us. So we finally have our metal. Woo! But the journey isn't quite over. What we get from smelting is actually a crude, kind of impure version. In the case of copper, it's called blister copper. And that's because as the molten metal starts to cool, trapped sulfur dioxide gas escapes, and it forms these little blisters all over the surface. We're close, but we need one last step to get it perfect. This last stage, it's all about purity. That crude blister copper, or any other crude metal for that matter, still has impurities mixed in. And to get the kind of high-performance metals we need for all our modern technology, we've got to give it one final, really thorough cleaning. This final step is called refining, and it is all about getting to absolute purity. The whole point is to remove every last trace of unwanted material. Stray metals, leftover bits of ore, anything that isn't our target metal. And depending on the metal, the methods can get incredibly sophisticated. Let's look at a particularly clever one called the Van Arkel method. This is what you'd use for metals like titanium, where even the tiniest impurity could cause a catastrophic failure in something like a jet engine or a medical implant. It's this super elegant process that actually turns the metal into a gas and then back into a solid, leaving every single contaminant behind. Okay, so here's how it works. First, you take your impure titanium and you heat it up with iodine. Only the titanium reacts and it forms this gas called titanium tetraiodide, while all the impurities just get left behind as solids. Then you pass this gas over a super hot tungsten filament. The intense heat literally breaks the gas apart, and it deposits this layer of ultra-pure crystalline titanium right onto the filament. And the best part? The iodine is released to be used all over again. It's brilliant. So now that we kind of get the process, let's look at an example that just shows how incredibly skilled ancient metallurgists were long before any of our modern gadgets were even invented. Let's take a trip to Delhi in India. 1600. That's how many years ago a truly remarkable iron pillar was forged in India. Just for some context, that's around the time the Roman Empire was falling, so a long, long time ago. So this massive pillar, I'm talking it weighs more than a large elephant. It's been standing outside, totally exposed to the elements. Sun, wind, you name it, monsoon rains, for 16 centuries. Any normal piece of iron would have turned into a pile of rust ages ago. So what's the big deal? Why is this one so special? That's the mind-blowing part. After 1,600 years, it shows almost no signs of corrosion. It's just standing there as a testament to the incredible, almost unbelievable skill of ancient Indian ironworkers. For centuries, nobody could figure out how they did it. Well, modern science finally cracked the code. The secret is this microscopic protective film called misoite. This super thin layer, which was created by the unique chemical makeup of the iron reacting with the local weather, acts like a permanent shield. The ancient ironworkers, they probably didn't know the exact chemistry, of course, but they managed to create a masterpiece that science is still learning from today. So, from the humble aluminum foil that we use every single day, which comes from that whole complex refining process, to an ancient rust-proof pillar that has baffled scientists for centuries, metallurgy is truly the hidden art and science that underpins so much of our world. The journey from rock to refined metal really is a story of chemistry, of physics, and of human ingenuity. And it makes you wonder, doesn't it? What other incredible hidden transformations are behind all the simple objects you interact with every single day?